For astronomers, this is one of the best observing sites in the world. I'm on Mauna Kea, Hawaiian for White Mountain. It's a volcano, hopefully an extinct volcano. And at 14,000 feet above sea level, it's the highest point in the Pacific Ocean. At this location, at this altitude, I'm above about a third of the Earth's atmosphere, and from here I can get views of extraordinary clarity. It's therefore not surprising that some of the world's finest telescopes are assembled on this mountain, and you'll be seeing some of them in the television programs. But for now, I want to make a few points about the videocassettes. These consist of a number of separate sequences, each of which is linked to a different section of the course. Some of the sequences help illuminate some tricky point or other, whilst other sequences add extra material. In all cases, we will be advising you in the printed texts when is the best time to watch a particular sequence. Many of the sequences are interactive, and all of them will benefit from more than one viewing. Do make full use of the S281 videocassettes. The project work is an important part of S281, and therefore I want to give you some assistance with it by walking through the observational part of one of the projects, the one in which you measure the difference in the length of the sidereal day, as measured by the stars, and the mean solar day, as measured by your watch. So, what's to do? Well, before you start any project, you should make sure that you first read the project book and study the appropriate project sheet. If you haven't already done so, then please do so now before watching the rest of this video sequence. Well, from the project sheet, you can see that what you have to do is to measure the time at which a star appears to move behind a building, so it's blocked from your view. This is because of the rotation of the Earth. You then repeat the measurement of this time on at least one subsequent night, and preferably on several nights, and then you analyze your measurements. Now, I've chosen the star Rigel as the star to observe. And the reason that I've chosen Rigel is that it's comparatively bright, easy to find, and is well placed in the evening sky currently. To check that it's well placed, I'm going to use the planisphere. So let's set the date, which is the 10th of February, against the time, which is 7 in the evening. And I can see that indeed Rigel is well placed. It's about a third of the way from the horizon to the zenith. As the evening progresses, Rigel moves westwards, and a few hours later it'll be about there. I can see what time that is. It's a little after 10 in the evening. Still well placed. So let's go. Well, this is my chosen observing site, and note that I'm well wrapped up against the February evening weather. Note also that I've brought quite a few things with me. First of all, there's the project sheet in there. I've also brought a torch, of course, and particularly my project book, something to write with, and most important, my watch, which I've set accurately before I came out. Now, my chosen vantage point is this post here. This is where I'll make my observations from, and that building over there, the edge of the BBC Open University building, is going to be the reference edge behind which Rigel will pass. Well, actually, it's not Rigel at all. It's cloudy, and so instead of Rigel, we're having to use an artificial star, a car headlamp bulb. It will do well enough as a simulation. Well, now I better start writing things down in the project notebook. First of all, today's date, the 10th of February, and then a sketch of my observation site. Plus the fact that I'm using Rigel and the building over there and so on. But most important of all, details of exactly where I'm going to place my eye. And what I'm going to do is to lean against this post, like this, and use my left eye to make the observations. And it is important that I write all that detail down. Well, let's get our star moving, and then I just have to wait and watch. Well, Rigel is approaching the reference edge. Now, what is it that I'm expecting to see? Well, Rigel won't actually just suddenly go out of view, and the main reason for that is that I can't keep my head perfectly still. So the effect is that Rigel sort of bobbles in and out of view. And what I'm going to do is to take the time when it's as often in view as it is out of view. Okay, let's do it. Right, here comes our artificial Rigel up to the reference edge. There it is now bobbling. Of course, the real thing would be rather different from this. There we are, that's about half in, half out, and now I want to record the time at which this is happening. Right, there we are. If I record the time to the nearest half minute either way, that'll be perfectly adequate. Well, that's it for tonight. What I want to do now is to come back here on at least one further night, and preferably on several further nights. I will then have all the data I require. The analysis of the data, this is described in the project sheet and also in the project book. And when you've got your measurements and analyzed your data, then you'll have your value of the difference between the length of the sidereal day and the mean solar day. Now, if you have any difficulty in understanding how the stars move and why there is the difference between these two day lengths, then you should certainly watch the next part of this videotape.
Imagine that this represents the Earth's globe. The vertical axis passes through the poles. This ring represents the equator. What would we see in the sky from this particular point on the Earth's surface in the northern hemisphere? From any such point, we can look upwards towards the local zenith, vertically above us. 90 degrees from our zenith, we have the horizontal plane that touches the Earth at the point. This plane stretches away to the horizon and divides the sky into the half that we can see, which lies above the plane, and the half that we can't see, which lies below it. To see what happens when the Earth rotates, we need some reference direction that remains fixed among the stars. Our reference direction goes from the center of the Earth, through the Earth's equator, and on outwards. Thus, as the Earth rotates on its polar axis, this reference direction remains fixed. Even though the reference direction is from the center of the Earth, the stars are so distant that this direction seems fixed among the stars even from the surface of the rotating Earth. Thus, if we zoom outwards towards the stars, the dimensions of the Earth soon shrink virtually to a point. To keep track of our earthbound coordinates, let's extend the rotation axis, the Earth's equator, the reference direction, the horizontal plane that shows which half of the sky we can see. To include some stars, I need to plot their directions on an imaginary sphere, the celestial sphere. The projection of the Earth's rotation axis intersects the celestial sphere at the celestial poles, and the projection of the Earth's equator forms the celestial equator. We can show the reference direction as a point A on the sphere, and in fact, our choice of reference direction means that this is the first point of Aries. Now let's add the directions to three real bright stars. North to the pole star in a direction very near the north celestial pole, then to Betelgeuse in a direction near to the celestial equator, and finally, below our horizon, south to Canopus. Again, we can show these directions as points on the sphere. Note that from our point of observation, the pole star and Betelgeuse are above the plane, so are visible, provided of course that the skies are dark and clear. Canopus is below the plane, so is not visible. Now watch what happens to our view of the stars as the Earth rotates. Let's hold it here. The pole star is still above the plane, so is still visible to us. Whereas Betelgeuse is just about to become invisible, it is setting. Canopus remains below the plane, so remains invisible. The Earth, of course, continues to rotate, but let's stop it once more. Betelgeuse is now rising to become visible again, whereas Canopus remains invisible and the pole star visible. Indeed, from our viewpoint high in the northern hemisphere, as our horizon rotates around the celestial sphere, the pole star is always visible in a clear dark sky, whereas Canopus is always invisible. What is our view of these stars from a different point of observation on the Earth? For a point just south of the Earth's equator, this is the horizontal plane that determines which half of the sky we can see at any moment. And this is the view from outside the celestial sphere. With our horizon in this position, the pole star is below the horizon, but Betelgeuse and Canopus are above it. Thus, from our more southerly point of observation, Canopus can now be seen. Some hours later, all three stars are below the horizon. Indeed, the pole star is now never visible. So, what we see depends on where we are on the Earth's surface. This is a long time exposure from a point on the Earth's surface, thus recording the apparent paths of the stars across the sky. You should now be able to understand this photograph. Test yourself. For example, the stars appear to rotate about a fixed point in the sky. In what direction does that point lie? It lies in the direction of a celestial pole. Replay the rotation animations if you don't understand this. In fact, this photograph was obtained in the southern hemisphere, so the fixed point is the south celestial pole. To conclude this sequence, let's consider briefly the difference between the solar and sidereal days. The sidereal day is the period for one complete rotation of the Earth with respect to the distant stars. The solar day is the period of one complete rotation with respect to the Sun, and it is different because of the orbital motion of the Earth around the Sun. This makes the direction to the Sun appear to move around the celestial sphere once a year. And here is our rotating horizon, rotating as the Earth rotates. Thus, the Earth has to rotate a bit further to catch up the Sun, and so the solar day is a bit longer than the sidereal day. In your project work, you should obtain a reasonable value for the difference in length between the solar and sidereal days. More broadly, you will gain direct experience of many aspects of the apparent motions of the sky.
This is the surface of the visible sun, the photosphere, upwelling cells of hot plasma like slowly churning porridge. Typically, each granulation is about 1,000 kilometers across, so if cells occupy about 1 million square kilometers, there must be about 4 million of them across the whole surface of the sun. And incidentally, this means that each one emits about a ton of radiation per second. That's a lot of energy to drive convection. And here is a computer-enhanced 3D view of the data. Watch the movement of imaginary corks floating on the surface. They gather in valleys between the granules, showing that there are larger structures stable on a lifetime of hours. We might think of them as a domain or family of granules within some convective structure. Now, if the sun had no magnetic field, there would be nothing else to see. In fact, we see a lot more different features, such as sunspots and huge prominences, moving along magnetic arches, some reaching hundreds of thousands of kilometers into space. This arch would easily encircle the Earth. And satellite detectors have recorded fierce bursts of X radiation against the darker photosphere, and sudden flares, seen here through a narrowband filter at a wavelength corresponding to hydrogen alpha light. These are all dramatic evidence of a sun whose magnetic field is highly active. This is a sunspot seen in hydrogen alpha light. Unlike most astronomical images, it's shown as a positive, so the dark center really does mean less hydrogen light from that region. Using, inappropriately, words from eclipses, these darker regions are called the umbra and the penumbra. But what does this sunspot look like in profile? Typically, the penumbra rises some 250 kilometers above the photosphere, whilst the umbra may lie in a depression as much as 1,000 kilometers deep. The magnetic field within the umbra is thousands of times stronger than in the surrounding quiescent surface, and this inhibits sideways flow of hot plasma. And this means, in turn, that not only the umbra but also the material just above it is cooler, and cooler plasma means we can see deeper, down to the 4000 Kelvin level. In the rarefied plasma above the sunspot, the temperature rises rapidly all the way out to the corona. And there's some small hot spots at temperatures of over 6000 Kelvin in the umbra too, but they come and go. So much for its structure. Let's look at its dynamics. This time-lapse movie clearly shows motion of plasma. First seen in 1908 by John Evershed, the flow is in two directions away from the crest of the penumbra. The surface of the penumbra may be rippled like corrugated iron sheets, and the flow shows where the magnetic field is roughly parallel to the sun's surface. Still unexplained, this Evershed flow is thought to carry away some of the magnetic energy until the sunspot just fades away. And so sunspots are rarely seen for more than a week or two, only sometimes coming around again as the sun rotates. Since sunspots normally occur in pairs, they have magnetic field patterns similar to the ones that we can make just by sprinkling iron filings over an electromagnet. The pattern shows how the field curves away from the intense regions at the poles. And if we look above the plane, we can see that the field arches up into space in great loops between the poles. Something like this is seen on the sun, but the magnetic sun is more complicated, a constantly changing mass of twisted and stretched fields interacting explosively with the plasma. And the magnetic field that emerges at the surface is only a part of the complex pattern generated by plasma flows thousands of kilometers below the photosphere, probably at the base of the convection zone. Although individual spots come and go over a matter of days in an unpredictable way, the total numbers follow a long-term pattern called the sunspot cycle. Sunspots start at high latitudes and gradually increase both in number and intensity. And as the months pass, they appear at lower and lower latitudes on each side of the equator. So a plot of their appearances takes on this form. It's often called a butterfly diagram. Each pair of wings of the butterfly takes about 11 years, but the sun as a whole reverses its polarity every 11 years, and so do the sunspots. If we take account of this alternating polarity of the spots, we see that it actually takes 22 years to come full cycle. This is the 22-year sunspot cycle. And there are other forms of activity which start at higher latitudes, overlapping the end of the previous cycle. The period's still the same, but if we include these extra forms of activity, the butterfly now has even longer swept-back wings. If we confine ourselves to a simple plot of sunspot numbers, there's data stretching back a long way. The 22-year cycle is always there, but the level of activity seems to change. Here's a long, slow minimum, for instance, another unexplained solar mystery. We have some better ideas about some of the faster changes. This is an H-alpha video movie taken at Big Bear Solar Observatory showing a flare, which is a sudden brightening across many wavelengths. Well, there are certainly rapid changes here, and they reflect changes in the magnetic field. This is a complex flare with many eruptive centers, so it's rather difficult to see what's going on. Let's look at a simpler example. Here's a nice pair of spots with the lower one fragmented and a stray one at the right. And here's how they line up with the magnetic field. We'll switch between them. Notice the opposite polarities. Now, here's the new part. Doppler measurements by astronomers at Lockheed's Solar and Astrophysics Laboratory show how the hot plasma is moving. Red means redshifted, that is away from us, and blue is shifted towards us. First look to the bottom right. Do you see the filament? Here it is again. See how it seems to untwist and goes crashing down to the surface. It's moving at about 100 kilometers a second. But now look towards the upper left, between the spots. There are some more blobs of matter, not all that big, but there. Did you see the flash? That was another flare. This time we'll catch it at the peak. may be small, but it shows clearly how the flare was triggered by the moving gas. Here are some radio images from the Very Large Array in New Mexico, and together they suggest that the activity starts at the top of the loop. Look at this diagram in your notes to see a possible mechanism for the flare. Here's a recent computer simulation of a way in which tiny ripples in the magnetic field can sweep particles along and so act as an efficient accelerator. Both electrons and protons can be accelerated by plasma waves like these to enormous energies, producing bursts of X-rays and gamma rays. Perhaps even cosmic rays originate in this way somewhere in the galaxy. In this video we've shown granules, sunspots with umbra and penumbra, filaments and flares. Now it's your turn to identify these structures in a couple of sequences from Big Bear. You'll see them as raw data, as the astronomer would, straight off the camera. Here goes. Now stop the tape and make your list against the clock reading. You'll find our list in the notes. We've seen various structures, flares and so on, and various phenomena, the sunspot cycle for instance, at different time and size scales. Here's a graph on logarithmic scales. It's reproduced in the notes. Try putting the various phenomena and structures in, each one at roughly the right part of the plot. Then put a ring around the ones which you judge as having no known explanation. Stop the tape and try it now. Then return and see our own plot. Good luck!
A map of the star-forming region in the Orion Nebula, made at mid-infrared wavelengths, gives a picture like this. The yellow and red areas are the places where the strongest infrared emission comes from. These are the protostars. The white contours mark the distribution of cooler, molecular gas. How do these clusters of protostars form? In Chapter 3 we learnt that stars form in dense molecular clouds, and that their formation can be triggered when parts of molecular clouds collide. A team at the University of Wales in Cardiff has been using computers to model molecular cloud collisions. Anthony Whitworth of the Protostar Group talked us through the simulation which results in star clusters remarkably similar to those observed in real life.
Here we see three subclouds of a giant molecular cloud, each of about 75 solar masses and about 3 parsecs in diameter, colliding almost simultaneously to produce a dense ridge of gas. The colors here represent how much material there is. Each pixel is colored according to how much mass there is in the column behind it. So the columns with little mass in them are blue, then those with somewhat more mass green, those with even more mass red, and the most massive ones are white. If we look right in the center there, we can see the very dense ridge of gas forming. The density in this ridge is about 10,000 times higher than the density in the original clouds, and the whole collision has taken about 1 million years.
The densities in the central ridge are so much higher than those in the original clouds that we soon run out of colours. So now we'll use the same colours to represent higher densities than in the earlier sequence.
The red gas here is rather denser than the red gas in the first run, where we saw the whole grain. And now the white gas is even denser still, and if we look very carefully we can see the white, very dense gas breaking up into small condensations, and these are individual protostars, rotating disks of gas and dust with masses in the range 2 to 30 solar masses.
Zooming in by another factor of 5 magnifies the picture 15 times relative to the beginning. Again, the densities represented by each colour have been increased.
We can see now about 8 or 10 protostars condensing out here. There's a certain amount of cannibalism goes on here. 1 or 2 of the protostars eat up their neighbours, so we don't end up with quite as many as there are originally. At the end, I think there are about 8. This arrangement of protostars in a long line is very similar to configurations which are seen in molecular line observations of the Orion molecular cloud and the Taurus molecular cloud.
A final zoom in on the filament shows the protostars interacting. The timescale of events here is shorter, a few thousand years rather than a million years for the cloud collision. The colours have again been changed to reflect even higher densities.
The densities at the centres of the protostars that form at the end are a factor of 10 to the 9 higher than the densities in the original subclouds that collided at the beginning. We can see 2 stars, that the top 2 have merged, or in the process of merging, and the large one at the bottom is also swallowing up some lesser protostars. Each of these protostars that you can see here, we're just isolating a small part of the ridge of protostars. Each of these protostars is a rotating disk supported by rotation in 2 dimensions and by pressure force in the 3rd direction. They have masses in the range 2 to 30 solar masses, diameters in the range from about 200 astronomical units up to about 800 astronomical units.
Now watch through the whole sequence again. This time we'll speed up the action. The end of the simulation might look like a cluster of stars, but there's still a long way to go. Before each is dense enough to begin producing light, there must be a further density increase of 100 billion-fold. Now return to your notes to compare this simulation with observed results. Other simulations by the Cardiff Group suggest that multiple systems are very common in young clusters of stars. This sequence shows the random collision of 20 clouds. We'll speed up this sequence in a few seconds. See if you can follow what's happening. You might like to go back and watch that through again. Well, what was happening? Let's review part of the sequence with Anthony Whitworth.
Observations of very young stars show that almost all of them are in, at least in binary systems. Many of them are in multiple systems. That's to say they have more than one closely bound companion. What we see happening now is the binary system on the right-hand side is about to merge, so the two stars combine to form a single star. But the binary system on the left-hand side is stable, and by the end of the simulation it's completed 6 orbits, and it's very unlikely to merge. So we end up with a triple system, close binary system on the left-hand side, and then a third star going round in a much wider orbit. And almost all the mass in the region displayed here is in the 3 stars. 80% of the mass is in the 3 stars. So there's very little drag due to the surrounding gas, and so the orbits of these stars are not going to decay. They will remain a triple system, 3 separate stars.